So today's topic will be partitioning for scalability in real-time streaming and big data applications built using Apache Apex. So I'll give you a quick introduction about our staff team. So I'm Vikram Patil, and I work as a software engineer at DataTorrent. I have Francis Fernandez with me, so who works as a software engineer and a contributor to the Apache Apex and the Apache Mala project. So he'll be handling the logistics for us today. And so we'll have a few breaks for the questions in between. So you can actually raise your hands or send a chat message for the other questions. So, and we'll try to answer those in the same meanwhile whenever we have a break. And at the end of the session, we'll have a couple of minutes as a question and answer session, and then we'll close the session. So let's get started now. So today's agenda will be introduction to the stream processing, who are actually new in the stream processing world, and then we'll go over how the Apache Apex is enabling the stream processing, and quickly over the application model using the Apache Apex, and then we'll look into the what do you mean by partitioning in terms of batch as well as in terms of streaming, and we'll look at the partitioning support in Apex. And finally, if time permits, we'll go over a few examples in Apache Apex through the slides, and probably a demo at our demo server. So what do you mean by stream processing? So in terms of, so you guys must be familiar with the batch processing, which is basically used by the provided by the popular MapReduce paradigm. But the batch processing is more of a done on the top of the data which is at rest or data which is pre-calculated, while stream processing is more of a data which is in motion, and basically the events which happens, and you process those events in very short time. So if you consider the stream processing, it's kind of a superset of batch processing. So the use cases which can be solved using stream processing, basically a batch processing can also be solved using a batch stream processing. So main notion of the stream processing has arise from the value of the data. So the value of the data actually degrades as the data gets older. And try to find the insights over created from variety of sources such as the IoT devices, Kafka topics, different files, like the files, basically log files which are generated from the web server logs or any of the application server logs, or the social media interactions such as likes on the Facebook, comments on the Facebook, or the tweets provided on the Twitter. So these data streams are basically unbounded and continuous. Guys, it seems like some of you are not able to see the slides properly. There is some kind of a delay happening. So just give us a moment and we'll get back to you again in a couple of minutes. Hello, sorry for the interruption. Actually, we had some internet issues, so we kind of needed to fix those. So I think it's resolved now. We can continue. So I'll start again. So basically, the stream processing, you guys must be familiar with the batch processing. So batch processing is more of a analyzing the data which is at rest, and where the data is actually pre-computed or pre-created, and then you analyze the data uh, which is already created. So while in the stream processing, you try to process the data as it arrives. So you can consider it as it's basically data in motion, and you try to find the insights over the data which is coming in. So so one notion you should, from the stream processing perspective, it's important to understand that value of your data actually degrades as the data gets older. So that's why this doing a stream processing is very much important. So from the stream processing perspective, data can come from the variety of sources such as IoT devices, Kafka, log files which are generated from your different servers, social media interactions such as comments and likes on the Facebook or tweets from the Twitter, or the post from the Instagram. So such type of data is basically unbounded and very much continuous in sense. So this data this data you can't really store this data and then process it later, because the value of that data degrades later on. So you can consider the batch processing as a kind of a subset of stream processing, where your data is already stored and you are processing. Those stream processing engine can actually satisfy the batch cases as well. At the same time, when you are doing a stream processing, you need to yield the results. So those results can be yielded at some point in the time. So that's why the stream processing engine also demands the temporal boundaries, where you can actually yield a different type of results. So there are different type of operations you can support on in stream processing, like such as aggregation and rule evaluation, and this constitutes your different type of streaming analytics. So, and at the end, once you are computed the results, they need to be stored somewhere or sent over to the next processing pipeline. So that's so all of this data has to be kind of processed at very low latency, because the next processing pipeline also needs to have a fresh data to process. So we have provided one example here where we are basically generating your web server logs and then putting them through the Kafka topic, and then the blue boxes are basically, you can consider as the stream processing application, where it reads from the Kafka, does the decompression or the parses the data which is coming in, or filter the data, and on top of that it tries to does the dimension aggregate, which can help you to find insightful insights from that. And once the insights are computed, they also need to be shown back to the user, or probably used by the another data processing pipeline, so we can again push back those data to the various Kafka topics. So now we'll just quickly go over the stream processing using Apex. So Apex, you can consider as an in-memory distributed stream processing engine. The Apex application, in the Apex application, the application logic is kind of broken into various components which we call as operators, and these operators are deployed across the yarn cluster. Yarn cluster. So Apex actually provides you a very simple programming model using a Java APIs, which can help you to develop your custom logic. Apex also allows you to define your state and the metrics in your Java member variables, which are actually checkpointed by Apex platform itself. So you don't have to worry about those the state if anything goes wrong with your operators in runtime. So we can restore from the checkpointed state, and again your processing can continue. Same thing applies for the metrics, where you can define the various metrics in your as a Java member variables, and those metrics are provided can also be provided for your different application for the visualization. Apex is basically a scalable and very high throughput and low latency implementation. So your operators can be actually scaled up and scaled down at runtime according to your load or your SLA. So Apex actually provides your dynamic scaling, which can help you to manage your throughput. At the same time, it also provides you the various type of compute localities, which help you to reduce your latency by avoiding by reducing your network bandwidth usage. So Apex actually supports thread local, container local, and the node local and rack local kind of localities, which help. So all of them are according to the so if you have an application which supports the thread local, then it's the latency is the lowest. Since basically the tuples are processed within the single thread. So next thing Apex supports is Apex is basically highly fault tolerant and ensures the end-to-end exactly one semantics for the correctness of your generated data. So in case of the node outages, Apex actually can recover the particular operator from the previously checkpointed states, which helps you to ensure that you don't have to reprocess from the beginning again. So this kind of incremental recovery has your application to restart from the failures, and again restart from the failures from the failed state and process the data further, and doesn't need to again restart the application entirely. So while doing this, so end-to-end exactly one semantics, it becomes very much important because of the replay of the tuples happens, but the platform has to ensure that your data is not generated twice to ensure the correctness of your entire pipeline. Apart from that, DataTorrent RTS actually from the operability perspective supports various monitoring and health monitoring and the management tools using an where you can actually see your visualization of various your matrices, as well as the various different type of data analytics, such as how many number of tuples are processed within certain time, what is the current latency of your operators. It also allows you to dynamically change your existing pipeline by pushing the various configuration values. So we'll just quickly go over the DataTorrent RTS product stack. So Apex is actually a Hadoop native implementation where and the Apex application you can consider as a yarn applications. So Hadoop infrastructure can be on-premise or on cloud. It can be anywhere, and the Apex core. So it basically on top of the Hadoop we have the Apex core runtime library, which is basically a core platform implementation which does the all checkpointing, recovery, and the windowing operations. On top of that, we have a development framework, which is the Apache Mallar operator library, which provides the various type of input operators and the output operators and the various type of transformation out of the box. So it has the JDBC input operator, Kafka input operator, which so basically you can use any of these operator and develop your application quickly and prototyping. So at the same time, Apex Apache Mallar also supports the high-level API for Apex. So normally the application development is done most of the time using a low-level APIs, which exposes the developer to a complex implementation in the Apache Apex core platform. So instead of that, we Apache Mallar also supports the high-level APIs, which basically abstracts out this complex implementation and helps the developer to quickly develop an application and test it out. So we are also working on the batch support. After the batch support implementation, you can actually run the your batch loads using a same framework. So next is the application templates. So application templates are basically developed, are kind of a use cases which we have seen at the various customers, and these are kind of a repetitive implementations. So we have decided to provide them out of the box, and where you can actually plug in your custom logic and uh, quickly get done with your applications. So next to that is the DataTorrent's proprietary implementation, where we have a GUI application library assembly, where you can actually build an Apex application using UI components which we have provided into DataTorrent RTS. And apart from that, we have management and the monitoring console, where you can see the various metrics such as how many number of tuples have been generated, how many number of tuples have been processed within the certain time frame. At the same time, you can actually even visualize the how your application looks like. So there are two concepts of application, like how your application logically looks like and how it looks like on the cluster itself. So apart from that, whenever you provide a custom metrics, you can even visualize those custom metrics using a real-time data visualization. So when we say the Apex is the native Hadoop application, so basically it runs as a yarn application. And if you look at the current diagram, you can actually launch an Apex application using Apex CLI as well as the DT console. So when you are launching an application, so you negotiate the basically resources. The application negotiates the with the resource manager and launches the stamp process, which is the streaming application master service. Once the stamp process is launched, it's responsible for launching a various basically containers, which actually holds your custom logic or the operator logics. So if you look at the current slide, you will see some ping blocks, which are your existing MapReduce containers from the different Hadoop application, while the green boxes are basically Apex containers. So there are roughly 6 operators in this current application. So 1, 2, 3, 4, 5, 6, and out of that 3 and 5 resides on the same node. So you can consider them as they are the node local operator. While at the same time you have a 4 and 6 which resides in the same container. So they can be either a container local or they can be a thread local. So which helps you to tune your application according to your low latency requirements. Is there any questions as of now? So we'll continue with the application development model now. So Apache Apex application more or less looks like a directed acyclic graph. So this graph, directed acyclic. So directed acyclic graph is more of a made up of the operators and the streams. So with streams you can consider as a sequence of data tuples. So basically once streams actually connects the two operators. So each of your basically operator you can consider it as your custom business logic in Java, and you can have as many instances of your, or so your custom business logic in Java, as well as your our built-in operator from the Apache Mallar library, or uh, and the operator can have as many instances as running in parallel. So each of these instances are more or less single-threaded implementations. So each operator basically has the can have a multiple input stream as well as the multiple output streams. And basically, after computing the receiving from the data from the input stream, you have to you can actually emit that particular generated data to the various output streams based on your logic. So, so when we say in the previous slide that your operator can have as many instances as possible, that's basically a partitioning of your logic itself. So when you have a data which you cannot process within certain amount of time, so that time you need to partition your data accordingly and process it parallelly to ensure to ensure your throughput requirements as well as the latency requirements. So in terms of batch, when you are trying to process the fixed set of load, you actually partition the data across your cluster and try to process it parallelly. Once when you process this data, so there are certain requirement in terms of batch is like your data should be easily splittable, as well as your computation should be as independent as possible. And at the same time, you should be able to merge the resultant data together again for the next set of pipelines. So similarly, when we consider the partitioning in streaming, so we don't we have to split the data, but you already have the multiple instances of your custom logic running. So you have to split the data and send the data to the various type of very different partitions of your same operators. Okay, so now we'll just go over the partitioning support in Apex. So basically, Apex allows you to have a customizable partitioning schemes where you can define your own data distribution policies. At the same time, Apex also provides one unique parallel partitioning implementation, which allows you to have a multiple independent pipelines of processing where from the input till the output, there is you can have a completely independent pipeline for processing. So next thing is that, like, once the data is computed by the multiple partition, you need to unify those the results and finally generate the unified results for the next operator. So for that perspective, Apex allows you to have your own custom unifiers, and which can basically does the job for you. At the same time, if you're not providing any custom unifier, then platform will insert in its own default unifiers in the system. Uh, Next thing is this basically Apex allows you to have a static and the dynamic partitioning where so in case of static, you can actually specify how many partitions for the particular operator you want and what type of distribution policy you want for the particular operator at the time at launch time. While in using a dynamic partitioning, you can decide the you can increase or reduce the number of partition based on the various type of metrics, various type of stats from the system or from external implementations. So there are two main kind of interfaces you can assume you need to implement to allow this dynamic partitioning implementation. Is like you need to implement the partitioner, which will partitioner is responsible for defining the new number of how many number of partitions you want, as well as the how you can actually do a state transfer between a multiple partitioner. So state transfer is important in case of the stateful operators where you are such as you can consider dedupe as one of the example of the stateful operator where you are deduplicating the incoming data tuples. So this so for deduplicating the incoming data tuples, you need to hold this in some kind of a hash map or something where you have a existing tuple stored, whatever the deduplicated tuple stored in your state. But when you partition this, each of this partition will process the different uh, ranges of your actual data stream. So in that case, you need to distribute your state across the different uh, partitions so that they can function properly. At the same time, at the same time, you need also to implement the stats listener. So stat listener actually defines when you want to trigger the partition. So stat listener is kind of allow you to listen for different statistics in the system, operator statistics in the system, such as what is the current throughput of the operator, what is current latency provided by the operator, and based on this statistics, you can actually make a decision whether you want to upscale, increase the number of partitions, or whether you want to reduce the number of partitions. So beautifully, the Apex actually provides you a separation of your custom business logic and the separation of your scaling decision. So all of the scaling decision most of the scaling decision can be managed through the platform attributes and or can be set from the configuration files. So you don't have to rewrite your business logic again and again. So we have some questions. Just let me go. Hey, so hi everyone. So we have a question from Satish. When you say split the data, are you talking about the stripping the data block into various nodes or keeping the different data blocks at different nodes? So the question is more of I think asked from the batch processing implementation perspective. So where you are actually dividing a data which is already created, but in case of streaming, the data is not already generated. So you are receiving the data on the fly. So when you want to split the data which is in motion, it's more of a based on different type of so Apex out of the box supports the hashcode based implementation for dividing this data stream to multiple partitions of the operator. But so this is the data is not already stored on the any node. This is more of a in-memory data which is flowing through your pipeline. Hopefully that answers the question. So we'll go to the next slide. So this is a kind of an will explain you better how the data is actually the stream can be actually split into a various tuple. So the tuple is basically a single atomic unit of your data which flows through your uh, processing pipeline, or you can see a DAG. And this each of the tuple for each of the tuple there is a decision is made which partition it should processed on. So the implementation is more of a looks like each partition has a kind of a fixed mask has been. So whenever we have the fixed number of partitions, so the last n bits of their hash code of the data tuple is basically used to decide which partition that tuple should go to. So when when the application is launched, or when basically a partitioning is done, so the mask value is generated. For example, in this slide, the mask is basically last 2 bits of your implementation, last 2 bits. Okay, I think I'll explain it again. So I think there was some delay in the slides. Basically what I was trying to explain here is like, uh, so the decision to which partition the tuple should be processed on has been made based on the hash code of the tuple. So when the partitioning is done, uh, basically we provide a mask for the tuple, for the hash code of the tuple based on the last n bits of the tuple. So once, for example, in this case, if you look at, there is a table which is provided bit for the mask and the partition, and then there is a tuple which is which for which we have to make a decision which partition it should be processed on. So once the hash code is generated for this tuple, the last two bits are masked using a provided mask, and the whatever the value is generated, this map is kind of used to decide which partition it should be sent to for processing. For example, in this case, the generated value is 0, 1. So that's why we sent it to the partition 2. So, but these decisions can be overridden by using by implementation of the custom StreamCodec. So StreamCodec is more basically responsible for making this decision, as well as it also responsible for serializing your tuples according to your own implementation. By default, Apache Apex supports the Java serialization based stream codec as well as the Creo serialization based stream codec. So you can actually extend any of this stream codecs, and then if you don't want to change any serialization, but rather you just want to implement the different distribution strategies. So so if you suppose you want to do a broadcasting of your tuples to all the partition, in that case, very simply you can choose your mask as a 0, 0, and then decide based on the all the values which you receive, you can send it to the different partitions. So this can be implemented as a custom distribution of your tuples using a custom stream code. Hello, I think there is some delay in the slides. Uh, it's kind of stopped completely. Hello, I think we are experiencing some kind of a network issues here. So, okay, I think slides are updated now. So we'll go over quickly to the static partitioning uh, functionalities which Apex provide out of the box, and then afterwards we look at the dynamic partitioning. So in case of static partitioning, so where you can simply provide a basically set the partitioner attribute on each of the operator, with the what type of partitioning, what are the different so Apex actually provides you out of the box various partitioners such as stateless partitioner, stateless throughput based partitioner, so and the stateless latency based partitioner. So you can provide this partitioner on any of the operators along with the how many partitions you want. So for example, in this particular diagram, uh, you can see the when you set the partitioner attribute with the value 3, so your physical implementation will actually look like the compute operator have a 3 different partitions. Once you have created a 3 different partitions, you need to unify data for the output operator. So platform itself will introduce a default unifier in your physical DAG. So when you have a, let's say, n by m partition, by normally what you can assume is like, for example, in the next diagram where you have 4 operators 0, 1, 2, 3 in your logical implementation, while in case of physical implementation, since you have a 3 partition for the operator 1 and the 2 partition for the operator 2, you need once the data is computed from the partitions of the operator 1, you need to unify that data and send it over to the operator 2. But uh, Apex basically introduces the 2 unifier to so that there will be no bottleneck in terms of unifiers, uh, and which also ensures that your half of the data will go to the one of the unifier and the rest other half of the data will go to the another unifier. So this helps you to kind of make it more fault tolerant, as well as the if this in any of this bottleneck unifier fails, then your all the uh, DAGs, which is after this unifier, has to be redeployed again. So instead of that, since there are 2 unifiers which are processing data at the same parallelly, so your bottleneck is removed. So this is how you can simply provide a static partitioner unit configuration file, where you can provide a stateless partitioner with the :2 as the how many number of partition you want. And when the application is launched, by default, the that many number of partitions will be created for the operator. So, and the next thing is below, what is mentioned is the stateless throughput based partitioner, where you can actually pass your operator. You can create it for your operator, and it takes couple of values such as cooldown milliseconds. This is the time which is between the 2 partitioning events. So this ensures that you are not doing a partitioning very frequently, because if the load is changing quite frequently, it might happen that the stat listener will trigger this partitioning multiple times. So, but you don't want to do this one into certain time frame. So this cooldown milliseconds will ensure that partitioning not happens frequently. Then there is a set maximum event API call, which ensures that once your maximum events goes beyond 30,000, at that point your partition will be triggered for the increasing number of partition. While at the same time, if your events drop below 10,000, your partitions will be reduced to a half. And then so you can set these values as a dag.set attribute, and at the same time you can do the same thing for the partitioner attribute. So next thing is the parallel partition. So parallel partitioning is kind of unique to the Apache Apex, where if you look at the first logical DAG and the DAG without parallel partitioning, so here you will see there are multiple unifiers which are inserted between 1A, 2A, and 2A and 3A. At the same time, 1B, 2B, and 2B, and 3B. So these unifiers are kind of redundant, and so you can actually get rid of them and ensure that you have 1A, 2A, 3A, which becomes your, as well as the 1B, 2B, 3B as the parallel pipelines. So parallel partitioning is helpful in case of scenarios such as data ingestion, where you are reading independently from various input sources and processing and transforming your data and pushing it to the different and the same output sources, but all of them is independent of each other. So it's very helpful in those cases. In such cases, even if you're one of, for the, if you look at the, even if in any of your pipeline fails, you still have the another pipeline available for processing the data from the same input source. So the next slide will show you how you can actually set the parallel partition. So for example, in the current slide, when you have a you want to set the parallel partition for the operator 2, so you have to set the partition parallel attribute on the operator prop attribute on the input port of the operator 2 to as a true value. So what it does is it ensures that the operator 2 will have the same number of partition as the operator 1. So the next slide will show you how we can set the partition parallel partition in the configuration, and the next slide will actually show you an example of the data ingestion pipeline which I was talking about, where it's very useful to have a parallel partitions. Now we'll take a quick break for the questions. If you have any questions, please type that in the chat window or raise your hand. Hey, so we received a question on slide 13, which says that since there are two unifier which are introduced into a now to avoid a bottleneck in the DAG, so whether the data will be sent to both unifiers. In normal cases, when there is no downtime for any of the unifier, the data will be split across the two unifier. But if any of the unifier is basically has some issues, then the data will be sent to the another unifier for the processing. So unifiers are more of a in terms of processing, they are independent of each other and they don't really depend on the state of your implementation. Hopefully that answers the question. Now there is another concept which Apex has introduced, which is a cascading unifier. So in terms of so cascading unifiers helps you to solve the cases where you have a huge number of partitions for one of the operator, and then there is a unifier which does the non-trivial computation, and it can become some kind of a bottleneck. In such cases, you can set the attribute with the unifier limit on the output port of the operator, saying that it can actually send the data to the only, let's say, you can set the limit on the unifier, so that ensures that your unifier can only accept data from only two input streams. For example, in this slide, it can accept k is basically your unifier limit, and your n and m is the n by m partitions, where n operator has the 4 partitions and the downstream operator has a 1 partition, while the k ensures that all of your unifiers are actually has only 2 input streams, and that's how the cascading if unifiers are introduced by the platform. So normally the unifiers are container basically deployed with the container locality with the downstream operator, so which also ensures the load on your network has reduced significantly. So this is how you can actually specify the unifier limit in your configuration. So you can specify the downstream operator name and the operator name and output port name, and at the same time unifier limit on the output port. So which ensures that your unifiers are cascaded using this limit. So you can actually provide an annotation which will ensure that there is no your particular operator is not partitioned. But when you are doing that, you have to ensure by default the operator should be partitionable. But when you are saying it's not partitionable, at that point you have to ensure the when there is a heavy load on your operator, it will break your latency requirements or throughput requirements. So in case of dynamic part, now we'll have a quick look at the dynamic partitioning and the requirement for the dynamic partitioning. So dynamic partitioning, in case of the state, when you don't have any kind of a state in the partitioning, it's very simple to do in your operator. It's very easy to do partitioning. But when you have some kind of a state, so that state has to be redistributed across the your implementation. So otherwise, your operator has basically will have a data loss, and so that is kind of you can actually do that one with the Apex, but this is more of a custom implementations. So if, for example, in this a slide where we have a 3 partition of operator B, and they have certain state associated with it. So when we introduce the one more partition due to a increased load or the for any reason of basically your latency is going down because the operator is taking more time to process it, or your throughput is reduced due to the processing time of your operator. So you introduce a new partition to the system, and at that point you have to redistribute your state correctly. So why do you need a dynamic partitioning? So these are kind of a use cases which you can consider where you have an uneven load throughout the day, and you can't really over provision for the your load, because that will lead to a lot of wastage in terms of money and the resources. So basically, whenever you need whenever you have a more load, you can actually increase your partitions for the particular operators as needed. So the same thing is like when your company is launched at the same let's say the application is launched in January, and you have a very good growth, and then by the end of next year your load is increasing. So for this kind of cases, you don't want to take your application down, rather you want to just add the resources on go, and your application should be able to scale up without any issues. So this is one of the good use case for the dynamic partitioning. At the same time, across the time, if your allocation is constant and your data increases, so your in data will overshoot your allocation, and which might lead to various failures in your processing implementations. So dynamic partitioning. So dynamic partitioning is basically your partitioning changes while application is running. So in this particular slide, you can see that your input operator 1A and 1B are constant, but on the next state, you can see the operator 2 is scaled to a 4 partitions. And since the operation 2 is scaled to a 4 partition, it also lead to an increase in the data which is processed by the operator 3, and which leads to a partition for the operator 3. So dynamic partitioning and can actually ensure the change in the number of partition at runtime based on the various statistics, or for the dynamic partitioning can also ensure that your operators are scaled according to the external triggers. For example, we have a Kafka input operator, which basically partition increases the number of partition based on the increase in the partitions in the Kafka broker. So as the Kafka partitions are increased, your Kafka input operator can automatically scale without any issues. So, and dynamic partitioning also support the redistribution of the state, and you can also provide your own custom partitioner for doing a dynamic partitioning. So we'll now look at the how dynamic partitioning works. So partitioning decisions are basically triggered by the stats listener. So stat listener, so you can actually implement the stat listener by implementing the stat listener interface, and you can write your own custom logic, which helps. So, but while you are implementing a stat listener, you have access to the various stats of operator specific stats or any custom metrics. So you can use those custom metrics or the operator specific stats to make a decision whether you want to change the number of partitions, whether you want to increase or whether you want to reduce the number of partition, or it can even so same implementation can be even based on the external implementation, external systems, such as what we have implemented in the Kafka input operator. So the Kafka input operator, what we have right now, supports the one-to-one partitioning or one-to-n partitioning, where your single Kafka, if there is a new partition being added to a Kafka, you can actually add a new partition for the Kafka input operator in case of one-to-one partitioning, while in case of the one-to-n partitioning, so one single partition on the Apex side can actually support the multiple partitions on the Kafka side. So we'll have a quick example on this one. In case of the stateful operators, so whenever the partitioning is being made, so it basically uses the last checkpointed state. So it has the ability, so your implementation need to have the ability to transfer the state from the older partition to the newer partitions, and so this is more of a custom implementation what you have to do to ensure your state transfer happens without any problems. So the steps which are being followed is basically platform will call the partitioner, and it will modify the physical partitioner. Partitioner will decide what are the different what are the new, how the new partitions will look like, or how basically your state is being distributed across the different partitions. So once this is done, so it's platform will basically modify the physical plan of your existing application, and it rewrites the checkpoints as per the new partition. It will undeploy the existing old partition from the execution layer, and it will once it is done, it will release basically require for the it will ask the resource manager to release the container resources, and it will deploy the new partition from, and it will start the new partition from the return checkpoints. So there will be no loss of data as such because of the good handling of the checkpointing system in Apex. At the same time, you can actually do an incremental operation. For example, in some of the operators, you don't have to kind of redeploy the existing old partitions. For those kind of implementations, you can actually just create the new partitions and basically initialize the state of those. So these are more like you can consider the stateless operators, or you can have a states which probably don't affect the due to introduction of the new partitions. So you can actually do that kind of implementation by providing a custom logic, and the engine will honor that. and it didn't want to redeploy the existing partition again. So this is a small code example where we have a stateless throughput based partitioner, which is actually extending the stats aware stateless partitioner. So here the method for the get load is leading to a decision which basically helps you to scale up or scale down the number of partition you have for the particular operator. So if your tuple process simple moving average for that particular window, it goes beyond the maximum events, then you are returning a positive value. If it below the minimum event, then it requests for the request to reduce the number of partition, and if it remains the same, then there is no change in the partitioning. So now we'll go with the few examples. So this is what I was discussing about in terms of Kafka input operator. So we kind of support two type of partition strategy right now, which is one-to-one partitioning, and the other is the one-to-n partitioning. In case of one-to-one partitioning, when you add a new partition to the Kafka, it actually automatically, Kafka input operator automatically creates a new partition in Apex. So next thing is the one-to-n partitioning, where your one input operator partition actually can be mapped to the multiple partitions in the Kafka. So this decision is done, like you have to just provide an what is the value of n, and it automatically does this kind of decisions. So this is the pipeline will look like with the parallel partitioning. And so when you have various partitions, and in terms of parallel partitioning, your one application will be scaled up with the same number of partition at each stages. So for example, here we have 3 partitions in Kafka topic. Now when we add when the partitions in Kafka increases, we actually end up adding a new pipeline. So this is more of a data ingestion kind of implementation, where you are reading from the Kafka and storing it to the file after doing the in between transformation operations. Now here we have a file reader partitioning. So user can actually specify the how many partitions require at the start of your file reading operations. So these are more of a input operators. So the functionality where you want to scale up the input operators based on the external events has to be implemented as a custom partitioners. So the partitioner and the stat listener, so they are responsible for checking with the external systems and deciding whether you want to partition the input operator further. So here you can specify the how many in case of the file reader partitioning, you can specify the number of partition you want to start with, and your your files from the particular directory will be distributed among these partitions. So this particular directory is actually monitored by the file input reader and file reader operator. When you change the number of partition at runtime, your new partition will be created automatically. You can simply increase the number of partition by setting the property required partition to some value, and it will increase the number of partition in the file reader operator. Once it gets redeployed, your remaining files from the same directory are distributed among the new partitions. So similarly, we have a block reader which basically reads from the very blocks in the files, and it follows the similar principle where you have you have to specify the maximum and the minimum number of partition you need. So as in when the new blocks are being added, your block reader will be partitioned according to the available blocks. If there are no blocks pending, in that case the partition will be released from and the resources will be returned to the YAML. So we'll quickly go over the one demo for the dynamic partitioning. So we have one example where we actually uh, kind of demo mobile analytics data, where we have a receiver which kind of receives the phone data and it try to find the locations from received phone data. So now what we'll do is we'll try to increase the physical number of tuples for one of the. So here we have a tuples coming in as 200 per second. So we'll increase this value to. So let me show you what the physical DAG looks like right now. So right now we have a physical DAX which looks like this, where we have two partitions for the location finder, and then we have a unifier for these two partitions, and the results are unified and sent to a location results. So this now we'll try to increase the number of tuples which are generated for at the input operator to 2000. Now, if you have any question, so right now once we update this one, it will take some time to for the physical DAC actually DAC to be redeployed with the increased number of partitions. If you have any question, you can ask right now. Question, is that just a multi-threading the unifier on the same machine? It's kind of not clear. Could you please, if you are asking that unifier or on this, the unifier is deployed with the operator. So yes, the unifier can be deployed with, is basically deployed on the same container as the downstream operator. It might be in the same thread or it might not be in the same thread. So that depends on the how you have specified the locality of between two, but it's more of a up to the platform. So there is another question, how this scalability depends on the RAM. So I think if your RAM usage increases, probably your number of tuples processed will decrease, and which will lead to lower reduction in the throughput. So it's up to you how you want to implement your partitioner in case of dynamic partitioning, while in case of static partitioning. So there are certain partitioner which are available out of the box, and they are responsible for uh, increasing the number of partition for the operators. So the logic for the partitioning can be anything. So if you want to implement your own partitioner and use it as in the static way, that is up to you. But right, so what we are supporting out of the box is more of a based on the uh, throughput based or latency based. And if the RAM is not available on the yarn, so your application won't be actually deployed. So there is another question whether there is any minimum RAM or predefined system requirements. So as Apex being a Hadoop native, so there are some requirements in terms of the resources, and you can actually tweak those resources using your configuration files. Uh, so you can provide how much minimum memory your application needs, or how much the minimum memory your container needs. So that is kind of configurable through the properties. So so yeah, now if since we have increased it to a 2000, you can actually see the your number of instances for the location finder operator has increased significantly. So I think 2000 is way beyond the limit of this. But this actually proves that your partitioning can scale up based on your incoming data. You want to ensure you can actually do everything is kind of customizable in Apex. So you can provide your own custom stat listener and the partitioner, and use any of the matrices to decide when you want to partition or how many partitions you want. So I think I'll just quickly once again go over the resources. You can reach us at users@apex.apache.org, or dtusers@googlegroups.com. You can read more about the Apex at apex.apache.org or more on datatorrent.com. We do have the free enterprise license for the startups and the startup accelerator pack. And for the bigger companies, we are coming up with the good licensing scheme which will help them to develop their applications quickly and also include the support from the DataTorrent. So do go over these resources and our YouTube channel with for DataTorrent. So on YouTube channel you will find the various talks from the conference as well as the various webinars. So please do connect with us with any questions you have, and we'll be happy to help you. So I think we'll close the session now. We'll wait here for a couple of minutes for the questions. So we do see some questions on the chat. It will be great if you guys can send us this question on users list, and we'll be happy to help you. So we are kind of running out of time now, so we'll now close the session. Thank you very much for attending the session, and hope you find the answers to the questions and it was interesting for you. Thank you.